The Wellington bomber stood on the hard surface at RAF Mildenhall, its fabric body shining faintly under the Suffolk moonlight on the night of April 3, 1941. Squadron leader James Ward and his five-man crew finished their pre-flight checks with the steady rhythm of men who had flown together for 8 months. They had done this 23 times before. Load incendiary and high-explosive bombs, cross the North Sea, find the target, drop the bombs, and return home. Tonight's target was Bremen, one of Germany's key industrial ports. Intelligence suggested that the flak defenses were weaker because units had been moved elsewhere. It sounded like a simple mission. What no one mentioned during the briefing was the heated debate inside RAF Bomber Command about the very plane they were flying. The Vickers Wellington had become the backbone of Britain's night bombing force, but it was still controversial among pilots used to traditional aircraft designs. The issue wasn't with the Pegasus engines or the guns, it was the fabric. While American and German bombers had shiny metal bodies that showed modern engineering, the Wellington was covered in Irish linen stretched over a strange metal frame that looked more like something supporting a greenhouse than protecting against bullets. Barnes Wallis, the engineer behind this unusual idea, had faced years of doubt from Air Ministry officials who couldn't understand his geodetic design. He explained again and again that the interlocking metal lattice spread loads evenly, making the structure stronger than it appeared. On paper, it was perfect. In the air, many pilots still looked at the fabric skin fluttering slightly in the wind and wondered if they were flying inside a death trap. Ward wasn't one of them. He had seen the Wellington take heavy damage over Wilhelmshaven in February when flak tore a hole through the wing big enough to crawl through. Yet it flew home smoothly. Still, he understood why some crews asked to move to Hamptons or Whitley's, which looked and felt like proper metal fortresses. At 2100 hours, the engines roared to life, drowning out any last-minute fears. Within minutes, Ward had the Wellington racing down the runway, lifting off English soil and climbing into the dark sky. They joined a stream of bombers heading east. Navigation lights went off as they crossed the coast. From then until their return, they were alone in a sky shared with German night fighters hunting bombers like them. Wallis's design calculations claimed the geodetic frame could survive far more battle damage than normal aircraft. Tests and models supported this. But tests don't shoot back. Tonight, over the heart of Germany's war industry, those theories would face the ultimate test, one that could either prove Wallis right or confirm every fear about sending men to war in fabric-covered planes. The first sign of trouble came at 22:45, still 30 miles from Bremen. The rear gunner's tense voice crackled through the intercom. "Skipper, we've got company. Looks like a 110, 7 o'clock high." It was a Messerschmitt Bf 110 night fighter, fitted with the latest Liechtenstein radar, able to detect bombers over 2 miles away. Ward pushed the Wellington into a shallow dive to gain speed, but the German fighter held every advantage: speed, height, and experience. The Messerschmitt opened fire from 600 yards with 4 7.92mm MG-17 machine guns and 2 20mm cannons mounted in the nose. Each cannon shell weighed 134 grams and flew at 600 meters per second, designed to rip bombers apart. They didn't just pierce, they exploded on impact, spraying fragments everywhere. The smaller machine gun bullets, firing over 1,000 rounds a minute, could slice through control cables, hydraulics, and fuel lines in seconds. The first burst swept across the Wellington's body from tail to middle. The thin fabric skin offered no protection. Bullets tore through both sides as if it were paper. The sound, survivors said, was like someone beating a drum mixed with firecrackers. Ward felt the plane shake, not from breaking apart, but from the violent shock of multiple hits. The navigator looked up from his charts to see starlight shining through fresh holes in the fuselage. But the German pilot had made one key mistake. He had opened fire too early, wasting ammunition while Ward threw the Wellington into a desperate evasive dive. Maneuvers. The bomber was slower than a fighter, but it could turn tighter than most pilots expected. Ward pulled back hard on the controls, lifting the Wellington almost upright and slowing it down on purpose to make the Messerschmitt overshoot. The German pilot committed to his attack run, shot past, and was forced to pull away to reset. That brief break lasted only 40 seconds before a second fighter appeared. Another Bf-1D-10 from a higher altitude, one that had been quietly tracking them for some time. This pilot was more patient, closing the distance to just 300 yards before opening fire. The closer range made his attack brutally effective. Cannon shells smashed against the geodetic framework, sending bits of metal spinning through the inside of the plane. One shell struck a main spar and exploded, the shock echoing through the whole airframe. Machine gun rounds tore across both wings. Some passed through harmlessly, while others cut electrical lines and pierced the fuel tanks. Then the flak began. Bremen's defenses had locked onto them with searchlights, and 88mm guns fired shells that exploded in timed bursts, meant to trap bombers inside boxes of shrapnel. Each blast sent thousands of steel fragments racing outward at deadly speed. The Wellington flew through 3 bursts, each one adding dozens of new holes to its already torn skin. The plane jolted and shook with every near miss, the pressure waves striking its fabric covering like invisible fists. Ward's instrument panel told a grim story. The airspeed needle jumped wildly from a damaged line. The oil pressure on the port engine dropped 10 pounds before steadying again, and the compass spun uselessly. Yet, underneath the chaos, Ward could feel something strange. The Wellington was still flying smoothly. The controls felt just as responsive as they had 20 minutes earlier. There was no dangerous shaking, no yaw, no sign the aircraft was breaking apart. The wireless operator, sitting in the widest part of the fuselage, watched bullets enter one side of the plane and exit the other, missing anything vital. One round chipped his desk and sent splinters into his logbook. Another passed through his hanging parachute pack. He could count 17 holes within arm's reach, each surrounded by ripped fabric fluttering in the wind. But the Wellington held its height and course as if untouched. The first Messerschmitt pilot, now repositioned, came in again from the left rear. He fired a second burst, about 120 rounds of cannon and machine gun fire. He watched his tracers strike home, saw fabric tear away, and pieces of the bomber's frame break off and fall into the night. In his report, 3 hours later, he confidently claimed a Wellington destroyed. No aircraft, he reasoned, could take that much damage and keep flying. Convinced he had just witnessed it begin to fall, he turned away to find new prey. But the Wellington wasn't falling. Ward had felt the hits, heard the metallic thunder of impacts, seen more warning lights flash on his panel. Yet the aircraft still held together. This wasn't luck or divine protection. This was Barnes Wallis's geodetic structure working exactly as intended. Every time a bullet broke one of the interwoven metal ribs, its load automatically shifted to nearby members. The structure absorbed damage like a spider's web. One thread breaks. It sags slightly, but 50 others take the strain. The second German pilot, far more seasoned, noticed something odd. He had destroyed 11 bombers before, and all behaved the same once badly hit, losing height, trailing smoke, or spinning out of control. But this one didn't. It just kept flying toward Bremen as if annoyed, not dying. Determined to end it, he lined up for a third attack, aiming directly for the engines and cockpit. Targets no plane could survive if hit. His third pass punched 47 more holes into the Wellington, 3 of them just inches from Ward's head. One cannon shell exploded against the main spar right behind his seat. The shock rippled through the metal frame like a sharp crack followed by a deep hum. Ward quickly tested the controls. They still worked. The frame was still strong. The German pilot, now nearly out of ammunition and fuel, stared in disbelief as his target kept flying on. Finally, he broke off and turned for home. A decision that would haunt him later during his mission debrief. The report filed listed it as a probable destroyed, rather than a confirmed kill. The Luftwaffe's intelligence branch, the Oberkommando der Luftwaffe's Technical Analysis Division, had been studying Wellington bomber designs since 1938, when the first production models entered RAF service. Their analysts, mostly engineers from Germany's top technical universities, created detailed assessments that circulated within Fighter Command headquarters. These reports included accurate data about the Wellington's wingspan, bomb capacity, armament, and ceiling. But they also contained one serious mistake. A misunderstanding that would prove disastrous for German night fighting tactics. A report dated November 19, 1939, document reference OKLIC 3-112, described the Wellington's construction method in dismissive terms. The author, an engineer experienced with the Heinkel 111's all-metal frame, called the geodetic structure outdated and more suitable for civilian use than combat. He wrote, "Fabric covering provides virtually no protection against modern weapons. The British reliance on this construction shows limited industrial ability, not a deliberate design choice." The conclusion advised pilots to expect the Wellington to fall apart quickly under concentrated fire. This view matched German design thinking. The Luftwaffe had gone all in on metal aircraft. The Junkers 88, Heinkel 111, and Dornier 17 were all made of aluminum alloy shells that carried their own load. These planes looked stronger, and when shells hit them, the holes stayed local. The rest of the metal kept the structure intact. German engineers assumed fabric-covered bombers would behave the opposite way, tearing apart after only a few hits. Night fighter pilots were trained accordingly. Manuals from the Nachtjagdschule, Night Fighter School, in Schleißheim instructed them to fire short, focused bursts at the fuselage. The reasoning was simple. No need to waste ammo on something that would break apart after a few dozen rounds. The method worked against other British bombers like the Armstrong Whitworth Whitley and the Handley Page Hampton, which used more traditional metal frames. Concentrated bursts easily damaged key structures, and the bombers fell apart mid-air or spiraled down. German pilots quickly racked up kill counts, confident in their tactics. But Wellingtons didn't die the same way. They came back home full of holes. Damage that should have been fatal. Reports began showing odd patterns. Pilots claimed they had scored solid hits, saw the fabric rip and parts fall off, but then lost sight of the bomber before confirming a crash. At first, intelligence officers blamed poor visibility or pilot error. The idea that their technical assessments could be wrong never occurred to them. Fabric was fabric, metal was metal, and German engineering was the best in the world. The truth that British design had outsmarted them never crossed their minds. Barnes Wallis hadn't intended to change bomber design forever. His journey began with lighter-than-air craft, specifically the R-100 airship project between 1929 and 1930. That massive dirigible, 709 feet long and filled with 5 million cubic feet of hydrogen, taught him a key lesson. Conventional structures weren't always the best. The R-100's internal frame used a geodesic pattern, interlocking spirals forming triangles that spread loads across the whole structure instead of putting stress on single points. When the airship pitched or yawed in turbulence, no single beam took all the strain. Dozens shared it together. Adapting that principle from an airship to a bomber required solving challenges that aviation engineers had never faced. Traditional planes used long beams called longerons running from nose to tail, with formers and stringers attached around them to shape the body. It worked, but it was inefficient. Traditional designs worked well enough but had clear weak spots. Heavy damage to one main beam could break the entire load path and lead to a total structural failure. Wallis suggested a completely new idea. Remove those long beams entirely and build a woven lattice instead, where every piece connected to several others, forming thousands of small interlocking triangles. The math behind his geodetic structure came from civil engineering, especially suspension bridge design. In a bridge, when one cable takes extra weight, others automatically adjust to share the load. Wallis applied that same logic to airplanes, using light metal strips arranged in two spirals, one twisting clockwise from nose to tail, the other counterclockwise. At every crossing point, the strips were riveted together, creating joints that could transfer stress in any direction. The result was a frame so strong that even if several parts were destroyed, the damage stayed local instead of spreading through the entire plane. The Wellington's fuselage was made from exactly 1,732 light alloy pieces, each one carefully shaped and heat-treated for the perfect balance between weight and strength. These weren't simple tubes. Their cross-sections were specially designed to stay rigid while keeping the structure lighter than a conventional frame of equal strength. Every single piece connected to at least 6 others, meaning if one failed, the overall strength dropped by less than 0.1%. What made it truly revolutionary was how it handled uneven stress, like the kind caused by enemy fire. If shells cut through parts on one side, the forces automatically shifted across the web to undamaged sections, even those on the opposite side of the fuselage. The frame didn't need the pilot to react or any mechanical fix. It healed itself structurally, by design. At first, Wallis's co-workers at Vickers laughed off the idea as far too complicated. Building more than 1,000 precisely machined parts into a 3D framework sounded expensive and time-consuming compared to the old method of joining long beams and formers. But the test results silenced the critics. The geodetic frame was lighter, tougher, and easier to repair. Damaged areas could be cut out and replaced without affecting the rest of the structure, something impossible in older designs, where long beams carried stress across the whole body. Ward flew the Wellington back across the North Sea at reduced speed, feeling subtle differences in the air. The shredded fabric made the plane slightly less aerodynamic, causing extra drag and mild shaking, but nothing dangerous. They had completed their bomb run over Bremen despite the fighter attacks, successfully dropping their payload before turning for home. With the compass destroyed, the navigator guided them using the stars. Soon the Suffolk coastline appeared in the distance. The landing went smoothly. At 2:30 a.m. on April 6th, Ward brought the bomber down with his usual steady touch. As it rolled to a stop on the tarmac, the ground crew approached in the dark, expecting another routine return. The engines shut off, the propellers slowed, and the exhausted crew climbed out to stretch their legs. Then Flight Sergeant Thomas Ricks, the crew chief, swept his torch along the fuselage and froze. The beam revealed not minor battle scars, but total devastation. The plane looked like a sieve. Ricks moved his light slowly from nose to tail, counting dozens of holes punched straight through both sides of the aircraft. Where cannon shells had exploded against the metal framework, the destruction was worse. Twisted metal, torn fabric hanging loose, and internal parts visible through openings that shouldn't exist on any flying machine. He began the standard damage report procedure, marking every hole with white chalk, numbering them, and logging each one's position and size. It was normal for bombers to return damaged, but when the count passed 50, then 100, then 150, the entire ground crew fell silent in disbelief. Routine work and simply stared. They had repaired bombers before, replaced damaged frames, reattached torn fabric, fixed instruments shot out in combat. But none of them had ever seen an aircraft come back from this level of destruction. The final inspection ended at 4:15 a.m., after 3 verification rounds to ensure accuracy. The total, 203 separate holes. 87 bullets had gone clean through the fuselage without touching any major parts, entering one side, flying through empty air between the geodetic ribs and exiting the other. 41 rounds had struck the frame directly, cutting through 11 members completely and bending or cracking 30 more. 19 cannon shells had exploded against the structure, tearing apart clusters of the metal lattice. The remaining 56 holes came from flak fragments that had riddled the tail and rear fuselage. What shocked the ground crew wasn't just how much damage there was, but where it was. The control cables running to the tail were untouched despite being surrounded by bullet holes. The fuel tanks in the wings had been hit 3 times, but the self-sealing rubber bladders had worked perfectly, preventing leaks. Some electrical circuits were destroyed, explaining the failed instruments, but backups had kept the flight controls working. The hydraulic lines to the gun turrets were cut, yet the turrets themselves still moved manually. Flight Sergeant Thomas Ricks circled the bomber twice, shining his torch across every surface, trying to make sense of what he was seeing. By any normal measure, this aircraft should have disintegrated over Germany. The sheer number of hits should have snapped enough load-bearing parts to make it collapse mid-air. Yet there it stood, its geometry intact, frame solid, still an airworthy machine that looked like it had flown through a storm of steel. Ricks made a decision that would have seemed crazy to anyone unfamiliar with geodetic construction. Instead of marking the Wellington as Category 3, a write-up that would send it for long depot repairs, he labeled it Category 2, repairable on-site within 48 hours. His reasoning was simple. The structure was still sound, and Bomber Command needed every aircraft available for the next night's mission. Losing one to long repairs meant fewer bombs over Germany, something no one could afford. 14 men were assigned to the job. Riggers, fitters, electricians, and armorers pulled from other duties or woken from short rest. They had about 4 hours to finish repairs before daylight risked exposure to enemy reconnaissance. They began with the structure. Each damaged geodetic member was checked for cracks or bends. If a member was completely severed, the fix was simple. Cut out the damaged part, insert a replacement section, and secure it using reinforced metal plates riveted on both sides. Then, they tested the joint under calculated stress. This was where Wallis's design truly proved itself. Unlike older frames that required disassembly to replace a single part, the Wellington's network of ribs let engineers reach any damaged piece directly. A fitter could cut out and replace a member in 20 minutes without touching the rest of the structure. The repair didn't even need to restore full strength, just enough to share its portion of the distributed load. Fixing the fabric skin was trickier. Standard practice called for cutting out damaged fabric neatly, then applying doped patches overlapping by at least 2 inches. The dope, a shrinking cellulose solution, would tighten and bond the patch when dry. For small holes, this worked fine. For the Wellington's hundreds of tiers, the crew had to improvise. Holes smaller than 6 inches and lying over the frame were patched individually. But where the fabric was shredded in large sheets, they replaced entire panels from spare material in the station's stores. Next came the electrical system. Every wire had to be traced, tested, and spliced correctly. Each broken circuit was identified and reconnected with proper insulation to prevent rubbing against sharp metal. The wireless operator's area was hit hardest. His communication cables were almost completely destroyed. The crew had to replace an entire bundle of 16 wires running through the geodetic frame to restore contact. The radio gear took the electrician an hour and a half to fix, working by torchlight in the cramped space and testing every connection one by one. By 5:00 a.m., the major structural work was finished. 11 geodetic members had been replaced, 32 reinforced with fish plate splices, and the frame tested by loading sandbags across the wings and fuselage to check deflection. The readings matched those of an undamaged Wellington, proving the repairs had fully restored its strength. Fabric patches now covered 197 of the 203 holes. 6 small ones on the tail were left, as they had no real effect on performance. At 8:00 p.m. that same day, barely 17 hours after Ward had landed, the same aircraft was ready again. A new crew under Pilot Officer Robert Chen prepared for that night's mission against Kiel's naval shipyards. Their Wellington, codenamed R. Robert, had only just been cleared. No one mentioned that its repairs had been finished 3 hours earlier, or that it had taken more than 200 hits the night before. Chen noticed the lighter-colored fabric patches immediately, scattered all over the fuselage and wings, with a few ragged holes still showing near the tail. He walked slowly around the bomber, touching the patches, and looked questioningly at Flight Sergeant Ricks. The crew chief's reply was calm. "She took some punishment last night. We've checked and replaced what was needed. She's as airworthy as any Wellington here." Coming from a veteran mechanic, that was enough for Chen. He'd flown Wellingtons for 6 months and understood how the geodetic frame made them tough. The patched skin even reassured him. It proved the aircraft had already survived worse. In fact, R. Robert was now probably the most thoroughly inspected bomber at Mildenhall, every part tested in the last 12 hours. At 8:05 p.m., the crew boarded. Chen started the engines, taxied out, and felt nothing unusual. The controls were sharp, the engines smooth, the new compass accurate. As he pushed the throttles forward, the bomber gathered speed confidently and lifted into the darkening sky at 8:37 p.m. They joined the formation heading east over the North Sea, then south toward the target. The radio worked perfectly, the repaired cables held, and the tail turret moved freely again. Everyone involved understood what this meant. Bomber Command was under relentless pressure to keep up its nightly attacks despite losses. Every plane kept flying meant one more blow against Germany's war industry. Being able to repair extreme damage at the base within hours, not weeks, was a massive advantage. R. Roberts' quick turnaround proved everything Barnes Wallis had promised. The geodetic frame could be fixed easily, its fabric skin patched with simple tools. Where metal-skinned bombers required special workshops, Wellingtons could be rebuilt overnight by ordinary crews. Crossing the Danish coast at 10:00 p.m., R. Robert flew flawlessly. The patches stayed tight. The frame carried all loads without strain. Far below, German night fighters were taking off, confident that British fabric-covered bombers would fall apart under fire, a belief that would soon cost them dearly. Ricks's incident report from April 7, 1941, spread quickly through Bomber Command. Air Marshal Arthur Harris, then Deputy Chief of Air Staff, asked for full documentation with photos and stress data. What made this case remarkable wasn't just the survival, but how quickly the plane returned to combat. The report became required reading at RAF technical schools, showing how the Wellington's design turned skeptics into believers. By mid-1941, so many similar stories existed that Bomber Command ran a full statistical study comparing loss rates. The results were striking. Wellingtons returned from fighter contact 63% of the time, compared to 41% for Whitleys and 37% for Hamptons. In cases of heavy damage, Wellingtons survived nearly twice as often. This was hard data proving the strength of geodetic design. German intelligence eventually realized their mistake. By late 1941, Luftwaffe bulletins revised combat guidance, warning that the Wellington structure was far tougher than expected, and advising sustained attacks on engines and cockpit instead of quick fuselage bursts. But by then, hundreds of Wellingtons had already made it home against all odds. The larger lesson was clear. A fabric-covered aircraft could outperform metal ones if its internal structure was smart enough. Though no post-war bomber used the exact geodetic system, it was too complex and costly. The underlying idea lived on. The concept of distributing stress and building redundancy became central to modern aircraft design. Planes like the American A-10 Thunderbolt, built 40 years later, carried the same philosophy. Duplicate flight systems, spaced engines, and frames able to take massive punishment. Aviation had shifted from "how do we avoid damage" to "how do we survive it?" A mindset change accelerated by the Wellingtons' record. Barnes Wallis was knighted in 1968 for his later work on the bouncing bomb, but his geodetic system may have saved more lives than any single weapon. Out of 11,461 Wellingtons built, analysts estimate its design prevented about 2,300 extra losses, roughly 13 to 800 airmen who came home because their plane refused to break, apart when physics said it should. That patched up. Wellington at Mildenhall on April 6th wasn't just a survivor. It was proof that real strength lies not in rigid armor but in flexible, well-distributed design, an elegant web of light metal wrapped in Irish linen, holding together against impossible odds through sheer mathematical genius.